Log on, tune in, find out. Another good idea from Cambridge.
He continues to talk on higher representations of the objects.
Okay, thanks. So today I will define some categorical object associated with Kac-Moody algebra or complex semi-simple algebra. Or you can even think of SL2, which is the case that Joe explained last week. And so I'm afraid the categorical constructions are going to, there's going to be some escalade. I mean, it's going to get a little bit higher, and I will need to use two categories. So it's not as bad as it might seem. And I would like to start with ordinary algebras, ordinary Kac-Moody algebras, and explain why, when you do representations theory of those algebras, highest weight representations, why you are really already looking at representations of a category. It's something very, implicit when you do the theory, but I'd like to make it more explicit. So I will be starting as yesterday with a Cartan matrix, symmetric Cartan matrix A. Let's say with I finite, really, today. And associated to that, there is a Kac-Moody algebra G. Sorry, let me say. Yesterday, yesterday I did introduce a Kac-Moody algebra associated to G, to this A, sorry. And the Kac-Moody algebras we use for representation theory are not quite the ones I introduced yesterday. The ones I introduced yesterday are the derived algebras of those I will define. And so the Cartan subalgebra gets a bit smaller than the one I introduced yesterday, and the representation theory is not really the one you want to study. So I introduced Kac-Moody algebras. They're slightly different from yesterday's, and they require a little more data. So you need root data, precisely, root datum. So consider a root datum, so I call it X and Y, yeah. A root datum of that type. So what that means is that you have two free abelian groups, X, Y. Free abelian groups, and you have a perfect pairing so a bilinear map that induces an isomorphism between Y and the dual of X and X and the dual of Y. So that's part of the data. And the other part of the data is the data of roots. So you want a map from I to X that sends we call alpha is the image of I, and a map to Y. Right, and I will assume that the images are linearly independent with linearly independent images. So set of alpha I is a linearly independent set in X, and set of alpha I Chech similarly, and such that. And that's where the type comes, that if you take the bracket of alpha I Chech with alpha j, you get aij. So the Cartan matrix is encoded in that data here. So that's the data that you get, say, from a complex semi-simple algebra. You do get such a data, and conversely, when you start with such an abstract data, you can associate a Kac-Moody algebra G. So there is an associated Lie algebra, curly G, which depends not just on A, but also on the extra data. And the derived algebra of G is the one I introduced yesterday, which depends only on A. So it is generated by objects EI, FI, same as yesterday. But now the Cartan subalgebra is a bit bigger. And I call the elements H zeta. So I is in I, and zeta is in Y. So there are certain relations which I mean, they are the same ones that you would use for say complex semi-simple Lie algebras or reductive finite-dimensional complex Lie algebras. And I don't want to remind you of the relations, which I did yesterday in the derived case. What I want to explain is that when you look at representations of G with a weight decomposition, then it's the same as looking at representations of a certain category. Another way to put it is that that's the way, for example, Lustig does for quantum groups, is to think of a completion of the enveloping algebra. So I won't do that. I will define instead directly a category. So it's curly U of G. So yesterday I used the normal U to denote the enveloping algebra. So now I am denoting curly U a category. So it's a C-linear category. And we define it as follows. So its objects so the set of objects is given. It's that set X. And now the maps are given by generator and relations. Or say arrows. So generators are small ei going from an object lambda to an object lambda plus alpha I. So that's for any lambda in X. So whenever you have a lambda, there's a map EI, which you should really probably call EI lambda. It depends on lambda, but for every lambda you have such a map. And you have a map Fi going the other way around. So these are the generating arrows for the category. And now there are relations between them. And the relations involve, so there are two cases. Well, they have to do with the bracket. Let me maybe write it like this. So if you start with a weight lambda, you can go to lambda plus alpha I minus alpha j in two ways. And when I is not equal to j, these two ways coincide. And when I equals j, you have to, there's a sign. So if you do ei fi minus fi ei, so that is an endomorphism of lambda. So now it's going to depend on lambda, the quantity on the right, and it's alpha h times lambda times the identity of lambda. Okay, so we have these operators moving between weights, and they satisfy these relations, and then they satisfy the, then you can put the Serre relation. So the Serre relation states that if you take the sum for A plus B equals 1 minus aij of minus 1 to the a e to the a f e to the sorry ei ej ei to the b, this is 0, and same with f, and again ei to the b with this parenthesis is the ei to the b, the b's power of this map divided by b factorial. So that defines a category by generators and relations. And now, instead of looking at representations of your algebra G or of its enveloping algebra, you can look actually at representations of that category. So if you're given, I think how do I want to put it? R a functor from that category U of G to the category of C vector spaces, C modules. So just a C linear functor. So careful, the category U of G is not a monoidal category, it's just a C linear category. So out of such a functor, you can define a representation of U of G. So the enveloping algebra of G acts, or the algebra acts on this big vector space, and the EI acts on a given R of lambda just by EI. And this way you get not all representations of U of G, but you get precisely representations which have a weight space decomposition. So maybe I can state it like that. So this gives an equivalence from the category of functors from purely U of G to C modules to U of G module with a weight space. So weight space decomposition means if you look at generalized eigenspaces of those H zetas, that your representation splits as a direct sum of such eigenspaces. Sorry, not generalized eigenspaces, but eigenspaces. Okay, so that's a very basic fact, but why I want to make it so formal is that when you're looking at representations of Lie algebra with a weight space decomposition, you're looking at more than a vector space. You're looking at a vector space with a fixed decomposition. So you're given not just V somehow, but the family of V lambdas, the family of those R of lambdas. Right, so now, and when you do think in these categorical terms, somehow the H zetas disappear. You only see X. Okay, so now comes the categorical version of that. Maybe I should say a word that what I've done here over C, you can, as I explained yesterday, you can take a Z form of the enveloping algebra of G, and correspondingly, there is a Z form of that category curly U of G. So you can take a Z linear subcategory, not a full subcategory, just a subcategory, by taking as arrows taking the subcategory whose arrows are generated by divided powers of the EIs over Z. So I should say, as a remark, there are Z versions. There is a Z version and also a quantum version of that. Okay, so now, now I have to go to the definition of that category, that two category A. So we'll define A with a double bar. A two category. So what I can say is that its sets of objects, or zero arrows, is just that set X. So what we will do is that if you think of this category curly U of G, so it has objects and arrows. Now we're going to define two arrows. So we're going to put arrows between the arrows. That's what makes a two category. So maybe I should tell you a reminder. So a two category is, well, one way to think of, well, let's say a strict two category, because it's what I will use is a category enriched in categories. So what that means is that it is a category where home sets are themselves categories. And such that composition of arrows is functorial, etc., in terms of those home categories. So to define a two category, you need objects. So in this two categories, the object set is just X. And the home set between two objects is not just a set now, it's going to be a category. And its objects are going to be products of EIs and FJs. And now there are going to be arrows in that category. Okay, so I should maybe finish these remarks by giving an example, the example of a strict two category. It's the two category of categories in a fixed universe. So objects are categories. And home, which I write as a curly home, between C and C prime is a category of functors. So when you have categories, you can look at functors between them, but now there are also natural transformations of functors. So there's one more layer of data. Okay, so now I get to defining these two categories. So the definition starts with our monoidal category B. So we have this K to start with, which is a polynomial ring, polynomial Laurent polynomial. And so everything is going to be linear over K. A is going to be linear over K, which means not that the home sets are linear, but these categories which replace the home sets themselves are K-linear categories. So we have already curly B is a monoidal category over K, generated by objects EIs, I in I, and then there are arrows xi from EI to EI, and tau ij from EIJ to EJI plus relations. So that's what I introduced yesterday. So now when you have that category, you can define a morphism. So B is a monoidal. You can take products. It's also linear. You can take direct sums. And you can define, what do I want to say? What do I want to define? What do I want to say? No, at that point, I think it's all I want to do, sorry. So I want to enlarge B by adding duals to the EIs. It's the first thing I want to do. So we need FIs in our category. So define B1 it's the K-linear. So everything is strict monoidal category. Obtained from B by adding objects. So we add Fi, a right dual, to Ei for all I. So that's I mean, in category theory, you can do all kind of formal constructions. You can take, you can invert any map. You can, I mean, you can, whatever you would want to do, you can do it. It's a very, it's a world that's soft enough. Except that in general, you really don't know what you get. I mean, you can get 0 or whatever. So here, I'm just, whenever I have an object, so I'm throwing in, I'm defining a new monoidal category, again, given by generator and relations. So my objects originally were direct sums of products of EIs. Now I can also take products of FIs. These are new objects. And so I have new objects in the category B1. And of course, there are also new arrows. And these new arrows, they come from, well, from this duality. So that means, so we have maps epsilon I that go from EIFI to 1. So our monoidal categories have a unit object and maps eta I from 1 to Fi Ei. So that's what the meaning of having Fi right dual to Ei means we're adding these Fi's to the monoidal category, and we are also adding those maps, and we're assuming, which means we're taking a quotient, we are putting some relations. We're assuming that the compositions, if you start with this object and go here, and then to Ei, so you can do that by applying first, you can think of Ei as the identity times Ei, and then you can apply eta I. Okay, I don't know why it's that. I think yesterday I had my cell phone in my pocket, so maybe it's better if you have something to just have no electronic device. Okay. So I have one way to go from EIFI, EI, another way to go back to EI by applying epsilon I.
The AI should be after.
That's completely right. So
The AI should be after the EI.
okay, that's here. We have to assume that this is the identity of EI. And same for if you start with Fi. So that's what dual objects, that's the properties of the dual object in a monoidal category. And you can formally add duals to objects in the monoidal category. You try to do that with a category of vector spaces and leave it as an exercise to see what you get. But you'll see that things can go bad if you do this formal construction. All vector spaces, not just finite dimensional ones, you can formally add duals to objects. So, good exercise to check to see what category you get. Okay, so we have this very big category. And so it looks like now like the full enveloping algebra. We have both EIs and FIs, or the curly U of G version, except that we should certainly put some relations. We've seen yesterday that the SER relations, the relations involving only EIs are consequent, are already true in B. So what the new relations, when you put E's and F's together, are these commutators, EI, FJ, which I just erased. EI, FJ is FJ, EI if I is not equal to J, etc. So how do we enforce? So now we want to enforce the relations EI, FJ. I and okay, so the first, so we could try to enforce that relation. It's not going to be an equality. It won't make sense. We should look for an isomorphism. And then the other relation is a bit more tricky because it involves an hi. There's no hi, and that's where we're going to take the model here, curly U of G. So we're going to build out of B1 a 2 category, which has a set of objects X. So let's. Sorry, what's the category?
Oh, you started off talking about you said A is a 2 category, and then you told us what a 2 category was. Is there anything more to say about A?
About A?
Yeah.
That's what I'll take the next 20 minutes here defining. So.
All right.
I'm sorry. Yeah, we will define. We will. I wanted to say what we're aiming for. Yeah, I'm sorry. So there are 3 steps. First step is to have something with the EIs. Well, 4 steps. Then you bring the FJs. So that's here. We have a category with both EIs and FJs. Now we have to enforce relations of that type. And also relations like EI FI minus FI EI is alpha HH lambda, say on lambda. We have to enforce this kind of relation. And so in this category B1, we could try to enforce such a relation, but this you need a lambda somewhere. So that's the first thing I need to do is to resolve that issue. So for that, let me define. So how should I say that? Let me given. So given, let's call it L, a product. Okay, so let's L be the subcategory of B1 with objects product of EIs and FIs. So I just don't allow the direct sum. So just a technical thing. So I just take products of EIs and FIs. Then I can define a map from objects of L. It's still a monoidal category, but it's not linear anymore. So I can go from objects of L to where can I go? I can go to X by sending. I can define a morphism of monoids. By sending EI to alpha I and FI to minus alpha I.
Sorry, what else is in B1?
So in B1, there are also direct sums of these guys. It's just that I want to do that, and otherwise there's a homogeneity issue there. So I should say full subcategory. Well, no, let's do it. Let's do it like that. So the idea is that I will need to pick up inside the B1 those objects that whose image under H is some fixed element in X. That's why I do that. Okay, so what else do I need to introduce? Oh, yeah, given now, given beta in X, we put B1 of beta as a full, say K-linear as a full additive subcategory of B1 with objects, direct sums of objects of H inverse of beta. So notationally a bit complicated, but it's quite simple. What I do, I just, whenever I have an element in X, I can take objects which are direct sums of products of E's and F, such that, well, the number of, if you look at H evaluated on a product, it's some fixed element in X. Okay, so that's now enough to define now a two category, not quite A yet. We define. So I put a double bar to the A. So it's calligraphic because it's a category, and there's an extra bar because it's a two category. Which you can do that in sort of in tech. So I define that. So it's a two category, a strict two category. Again, everything is with objects is X. And now I have to tell you what is the category of arrows from a weight to another weight. And that's B1 of lambda prime minus lambda. So it's a fairly inoffensive construction. I just want to do something similar to what I had done with the with construction of curly U of G of this category out of the enveloping algebra. So here I take a category where the objects, two categories, the objects are weights, and between two weights, I put a category, and its objects are sums of products of E's and F's, with whose H is lambda prime minus lambda. And between these products of E's and F's, there are arrows, which are the ones you get in B1. So B1 is just way too many maps in B1. We need to put relations, but we will need this category A1, this where we have this level to put the map, to put the relations. Okay, so we're almost at the point where we can define A. So to define A as the last ingredient, as I explained, what we want to do is to enforce those relations. And so equality is not a good idea in a category or in a two category, wherever it's happening. If it's not a set. So instead of trying to get EIFJ equals FJEI, we should enforce that a certain map between these two objects is invertible. So we need to produce a map between EIFJ and FJEI. And so that comes from constructions we did in SL2 with Zhou Shuang. So the way it goes is as follows. So we define sigma ij. It's going to be a map from EIEJ to EJEI. So you can think of it as living in the category B1 or living in some Hom space, Hom here, which is itself category inside B1. So it's defined as follows, as a composition. So okay, I'll write it, and then I'll explain. Okay, that's not right. Something funny there. Okay, that's not right. I want to do a bracket between EI and FJ. Okay. So the map here is defined as a composition. So we can go from EIFJ to this product by thinking that we have the identity here, the unit object, and we are applying eta j, and then the identity of that object. that takes us here. And so we can go back from here to here by applying, using the fact that fj is right dual to ej. So we're using duality to define those maps, duality between E and F. And now we have to fill in this middle map. And we need to go from EJ, EI to EI, EJ. And we have a part of the data is precisely a map here. So here we put Fj, tau j I, Fj as a map there. So in other terms, the map sigma ij here is really defined out of tau ij by adjunction, if you think of, or duality. Okay. If you think of all these objects as vector spaces, so we have various tensor products of vector spaces and duals, and you can see easily that out of a map from EJ to EI EJ, you get a map from EI times the dual of EJ to dual of EJ times EI, just by taking adjoints of maps. Okay, so we have this map sigma ij, which is good. And so to enforce the first relation, we're going to force that map to be invertible. So it's if you have a a commutative ring and an element in a commutative ring, you can define a new ring where you have inverted that element. So if you have non-commutative rings, then things go bad. But if you have more general things like categories, then things don't go bad. You can just invert maps and then ask what you get. But so here you can just formally add inverses to these maps. And, that's one step. And the other step is the more complicated relation EIFI minus FII equals this number on the right. So the number on the right, so again, in a category, you cannot take difference. In a linear category, additive category, you cannot take differences of objects. You can take just sums of objects. And so we have to put all, this term with a negative sign to put it on the right. And this alpha HH lambda is either positive, negative, or 0. Anyway, so we have to put it in the right side. So depending on alpha HH lambda, we're going to need to do different things. So if alpha HH lambda is greater than or equal to 0, we define a map rho I lambda going from EI Fi. So now this would make sense already in B1. But what I mean, it doesn't really matter if you think of it as a one arrow in A1, a two arrow in A1. It doesn't really matter to which object where you start. But now for this map, we have a dependence on the weight. Okay, so I insist here it's in A1. So Fi is a map from lambda to lambda minus alpha I. EI goes back to lambda. So I should say restricted maybe to, I will maybe put one lambda. So that means we are looking at EIFI as a map from lambda to lambda. So we have this category of the endomorphisms of maps from lambda to lambda, and we're looking just at the objects in this category. And we're saying that two objects are isomorphic. And for that, we define a map. So it's going to be defined as follows. Well, might as well write it as a product. Okay, so there are two endomorphisms of lambda that are equal. One is EIFI, and the other one is a direct sum of two things, FII plus alpha HH scalar lambda times times 1. So now this is taking place inside a category. This takes place in this endomorphism category of lambda. So that's taking place inside inside an additive category, inside a k-linear category. So I have to be careful. These are not scalars. These are objects in some category. So I need to tell you what this map is. write the formula for that map. So going from EI-FI to FI-EI, well, we do have a map. It's sigma II. So we define that map as sigma II. So far, we have used our taus to define sigma ij. So tau is really what leads to sigma ij. And the category B had also x's built in. So we need them to define maps from EI-FI to 1, to the identity of lambda. And there is because Fi is dual to EI, there is already a map from EI-FI to 1. So we need many maps. So one typical map we can use is this map epsilon I, which takes us from EI-FI to 1, but we need more than one map. We need a certain number of maps. So what we can do is compose first, apply first an endomorphism of EI, a certain power of x. So it's going to be a sum over R of EI times EI composed with xi to the R times Fi. So we start with this product of EI and Fi. We apply an endomorphism given by a power of xi on EI, and then we use the duality to get to 1 lambda. And you take the sum from R equals 0 to alpha h lambda minus 1. Right, so that's a map that uses both x and tau, so that's good. We use what we have put in the category. And now the definition of these two category A, finally. So A is obtained by starting with A1 and inverting the maps sigma ij. That's when I is not equal to j. And inverting, so I have defined only the map when it's non-negative. When it's non-positive, you have to go in the other direction. And there is a similar formula where instead of epsilon I, you use eta I. You use the duality to go from FI to the identity. And we need to invert these maps as well. So that's the category, is the two category associated say with G. So when you have a Kac-Moody algebra, symmetric or, I mean, symmetric assumption doesn't play any role in the theory. You can do that in for a general Cartan matrix. You get two categories. So you have as objects still up there. The objects are just weights. So now at the next level, when you have two weights, you have a category of homomorphisms, and its objects are products of E's and F's and sums of those. So that's still quite natural. So the next level is that between such one arrows, there are two arrows, and they come from the x's, the taus that were in B, but also from epsilons and etas that I needed to add to get f's. And there are even more maps in some sense because I have inverted these things. So probably should say that. So the object, the zero arrow, one terminology would say that the zero arrows are given by x. One arrows are sums of products of EIs and FIs. And two arrows, that's where there is some interesting stuff. Two arrows, they are generated by xi's, tau ij's, epsilon I, eta I, and you have also to throw in these inverses. So So at that level, we have just this set of weights. Here, we take products of E's and F's, so it's like working in the enveloping algebra of our Kac-Moody algebra, Z form maybe of that. It's still not scalars, these are objects, and the scalars come only at this higher level. So there's this higher level where you do get scalars, there's some kind of higher symmetries eventually. And these x and tau, they satisfy certain Hecker relations. So we've added a layer of information which is of Hecker type. Okay, so now I should say what is the precise relation with the enveloping algebra of G. So you can ask what are exactly what spaces you get, spaces of two arrows between two products of E's and F's. You can ask the question, but it's rather unpleasant, even for SL2. It's some kind of recursive, it's a highly recursive definition, and things don't commute, so it's get very complicated home space. So, for example, the homomorphism rings. So if you take a product of E's, earlier on in the category B, the homomorphism ring was just one of those Hecker algebras I introduced on Monday. Now what you get in this bigger category as an homomorphism ring of product of E's is some non-finitely generated algebra. So you get, typically you will get polynomials in infinitely many variables. Okay, so what did I want to say? Oh yeah, relation between U of G and this two category. So out of a category, you can get a set by in various. I mean, you can take isomorphism classes of objects, or if it's an abelian category, you can take its K0 or even an additive category. So out of a two category, you're going to get just an ordinary category. So how do we do that? Well, first, if I really want to link to U of G, I might as well link it to the Z form of U of G. And we saw already yesterday that if we want the Z form, we have to introduce divided powers, which means that we have to take not just sums of products of E's, but also direct summand of those. So we should really take the idempotent completion of these two categories. So we put I or idemp as idempotent completion. Okay, so that happens only at the, what we're doing is that we're completing the home categories in these two categories. We're not doing anything at the level of 0 arrows. So that means we're adding direct summands of products of E's and F's. So then we have divided powers, and what we can do is take. Okay, do you have a notation for that? No, I don't have a good notation. So let C be the category with objects X and home from lambda to lambda prime is going to be the Grothendieck group of the category of homomorphisms in A idemp from lambda to lambda prime. So what that means is that given a lambda and a lambda prime, we're looking at, we're considering an abelian group which is generated by direct summands of products of E's and F's. That's the generators, isomorphism classes of these guys. And as a relation, we say if the sum of two objects is a third object, then we're putting that relation in this abelian group. Okay, so now we have this category, and we can ask what this category is, or what it's related to. And because we have started with a category with set relations, and we have put f's, and we have added the relation EI, FJs involving commutators of EIs and FJs, we do get the following proposition. So everything is somehow obvious there. Is that there is an say an isomorphism of categories. Once in a while, categories are isomorphic, going from. Oh, sorry. Do I mean that? No, there is I should say there is a functor first. First statement is a functor. So there's a functor first, starting from this category curly U of G to that category C, given by, well, lambda maps to lambda at the level of objects. So we have two categories with the same set of objects, and at the level of maps, we send EI goes to the class of EI, and FJ goes to the class of FJ. So what I'm saying is that whenever there is a relation holding in the enveloping algebra of G, or in this categorical version, it's going to hold in this category, these two categories, at least if you identify the class of an object with the class of a direct sum. So there is a functor like that, just the relations hold. And now this functor is an isomorphism of categories. If we tensor over K with Z. So here it's UZ of G, I should say. It's a Z form. We are not allowing arbitrary direct sums of, we cannot multiply by complex numbers, those EIs, that we can only multiply by integers. And it induces CZ is same with this category. So remember, we have this ring with many indeterminates, and we can there is a nice specialization of these indeterminates depending on a quiver orientation. So given orientation of the quiver whose underlying graph is determined by the Cartan matrix, we have a specialization of K, so we get a two-category defined over Z, which can be studied. And now, if you look at the Grothendieck group of that two category, it's still a category defined over Z. I mean, the Grothendieck groups are over Z, doesn't really matter. Now, one can prove that it is an equivalence. So that's a little more precise. But I mean, somehow, I should maybe not have confused you with that, because it's doing this base change is a bit confusing here. I think it's just look at, I mean, this is really what is important, is that the relations that hold in the enveloping algebra do hold in our two category. Potentially, there could be more, this map, I mean, there could be more relations in this category, potentially, or there could be more objects here. Well, I suppose it extends uniquely, but let's put it. Yeah, that's probably better. It extends uniquely to the divided part. But you're right. That's not. Yeah. Yeah, that's a good point. Yeah, thanks. Yeah, you're bringing an important point. Is that because Fi is the right dual to EI. The homomorphism ring of Fi is isomorphic to the homomorphism ring of EI with the opposite multiplication. And so we use the nidempotent to define the divided power. So we can also take nth power there. Fi to the n is right dual to EI to the n. So we had an idempotent yesterday in this homomorphism ring. So we take the same idempotent there to define Fi to the n. So indeed, it's the Fi and EI play completely symmetric roles. And so we use that to define divided powers. Okay, so I think that's basic things one wants to say. So, so the construction is maybe not as bad as I mean, you can give much worse, much more complicated constructions of slightly different categories. There are variations that are much more complicated, which I will not talk about. So the point is that this is a very complicated, this is an unpleasant definition. And what's unpleasant with it is that it's quite hard to study representations of these two categories. So if you want to study categories acted on by these two categories, then it's quite hard. It's very hard because it's easy to make A1 act. You just have to produce EIs and adjoints FIs and various maps, and it's all fine. But the problem is the step going from A1 to A. So an action of A is the same as an action of A1 in which certain maps are invertible. And if you take the basic examples that Cho gave last week of representations of symmetry groups or Hecker algebras, in these basic examples, there is no direct proof, as far as I know, that those maps are invertible. So you do need to do something about that, and that's exactly why this other formalism that Joe explained last week is useful. So you have a formalism, you can replace checking that those maps are invertible, which is really hard, by checking that such equalities, that the fact that this map is an isomorphism, you can deduce it by the fact that, well, of course, it would be a first reduction would be to say it's enough to check that these two objects are isomorphic, but that's still almost as hard, probably even as hard. But it's enough to check that at the level of suitable Grothendieck groups they are isomorphic. So if you let these functors act on algebras, you would have to prove that by applying these functors to modules, to a first module, same module here, you get isomorphic modules, so it would be very hard. It's enough to prove that the classes of these modules in the Grothendieck group coincide. So that's an important point. So I will discuss that tomorrow. So I should say why one wants to consider these categories. So what's interesting about, one point of interest about complex semi-simple algebras or Kac-Moody algebras is not just the algebras, but their representations. So it's the same here. At least from my point of view, that's, so Kovanov and Loda looked at these half things, and they were really interested at the structure. So from my point of view, it's more, my interest is in the representation theory. So what we'll study tomorrow is, you can look at called two representations of those categories, which means, so if a representation of an algebra is just a morphism from this algebra to endomorphisms of a vector space. Earlier, we saw a representation of a category. We had this category curly U of G, and a representation is a functors towards C vector spaces. So now a representation of a two category is going to be a two functor from these two category to, well, we know a basic example of of category is a category of sets. The linear version is a category of vector spaces. Basic example of two category is a two category of categories. Linear version of that is, well, some various choices. You can take the two category of additive categories, the two category of abelian categories, of triangulated categories. So possibility is to go to the two category of, say, additive categories, say K-linear in this case. Or you can go to the two category of K-linear abelian categories, or two category of K-linear triangulated categories. Those are various possibilities. Various types of two representations. And I mean, this last level is not very satisfactory. You should really think of DG categories or infinity categories. So last week's lectures of Joe was, as I will explain, was the study of SL2 categorifications is essentially equivalent to the study of two representations of that two category, the case of SL2, very basic Cartan matrix, two representations with values in nice abelian categories. And somehow the whole theory and of those two representations and the structure even of those two categories, you need to check properties, and a lot of them can be reduced to SL2. And like in classical study of structures of enveloping algebras of, say, complex semi-simple algebras, there are many things that reduce to SL2 and even to representation theory of SL2. So there's something similar here. You have to know quite a bit about the SL2 categorifications to get to prove the properties you need about these two categories A's or these two representations. So that's what I will try to do tomorrow. So whereas these categories, these two categories is complicated, this studying these two representations is not that bad. So it's, and maybe, well, okay, while I'm there, I should say that a category of representations is a category, and the two category of two representations is a two category. So you look at these things, those are two functors, whatever it means, which I will explain tomorrow. So there are maps between two functors, and there are maps between maps of two functors. So if you go from, anyway, so that's what happens. And so that you have two categories there. And so that forms the set of these two functors in either of those that gives you a two category. And in relation with Sasha Gleshev's question yesterday, when you have a Lie algebra, you have a tensor product of representations. So that equips a category of representations with a tensor monoidal structure. And so these two categories here, I mean, not you have to go into a suitable target, DG categories or infinity categories, can be equipped also with a tensor product. So these two categories eventually, suitable in a suitable setting, can be equipped with this extra structure of tensor product. So you can take tensor products of such two functors, whatever it means. And so that's like in usual representation theory, you can use tensor products to build new representations. There's something similar here. You can use tensor products to build more two categories, which means more categories acted on by A. So that's all for tomorrow. So today, tomorrow is going to be a bit more concrete. So no more two categories. Okay, thanks.
So when you took the idempotent completion in A, you did this after you put the E's and F's together?
You don't, I mean, the only thing you really need to add, you only need to add images of the BNs. And when you look at taking the idempotent completion of a category represents a two functor, which is, it is the adjoint, it is the two adjoint of the functor of the inclusion of the idempotent complete categories inside categories. So what that means is that if you're looking at actions of these two categories on idempotent complete categories, like Abelian categories, then it doesn't matter if it's the same as looking at actions of the idempotent completion of A. That's what this adjoint property says. So it doesn't really matter if you idempotent complete or not when you look at representation theory.
Can you elaborate on the differences in the definitions? Like you used a different definition of Kac-Modelli algebra.
Yes.
Yesterday.
Yes.
Can you say something about that?
Yes. So the one of yesterday is just a derived algebra.
Oh.
So you can define a Lie algebra with EIs, FIs, and H's. So the H defined are going to generate a commutative subalgebra, this H zetas. And when you take the derived version of that, you get the subalgebra generated by EI, FIs, and that's it. So inside your Cartan subalgebra, all you get are these HIs, and they never fill the whole of this Cartan subalgebra unless you are in the Dynkin case. And your algebra, yeah, and you start with something with semi-simple XY.
Should be non-degenerate.
Exactly. Oh wait, in the symmetrizable case. No, the radical. You want the intersection with the radical to be the wet. I don't even. I mean, that's not even part of my setting there. But so it's just a derived subalgebra. So in the finite dimensional semi-simple case, the two are the same. For SLN, the two algebras are the same. But if you take SLN hat, for example, the affinization, then you will get a proper sub-algebra whose representation theory is not quite as nice. The highest weight, I mean, you don't have a good weight theory, you don't have enough. So your commutative subalgebra is too small.
Thanks. Yeah.
Maybe I forgot something, but what about the third relation in the category U of G?
The Cartan relation?
Yes.
The third relations, you mean?
Yes.
Oh, they already, well, there are two things I should. So they already hold in this category B that I defined yesterday. I explained that they are true. But on the other hand, it is the fact that there will be automatic, you don't need to check them. If you take a highest weight representation of, say, a complex semi-simple Lie algebra, when you want to construct such a representation, you need EIs and FIs and their action, and it's enough to check the relations that EI and FJ is equal to HI. The set relations are a consequence. So when you have add EI to some power applied to J equals 0, is a consequence of looking at the representation of the SL2 generated by EI, I suppose. So it's SL2 representation theory tells you that the set relation is automatically fulfilled somehow on nice representation. So in some sense, you don't have to worry about it.
In SL2 categorization, we ask F to be right.
Yes.
So here, F is just right.
Yes, this is somehow the main difficulty of what goes next in the theory. That's the main issue. That's yeah. So I will show that if you act, I will show that basically it's almost true that F will be left dual already. It's automatic because it's automatically true. It's almost true. It's not quite true in this category A. You have to take a suitable completion of A, but in a completion of A, F will automatically be left adjoint. So if you take Joe's point of view of SA2 categorifications, you take E and F left and right adjoint, and you put conditions on K0. In this approach, you put much stronger conditions by requiring invertibility of these guys, but you don't ask for the left adjunction. That left adjunction is a consequence. That's a tricky point.
And it's a natural left adjunction. It's not just there's an isomorphism.
Yeah, exactly. Okay. But somehow you see the fact that it's natural means that you should not impose it. You should not put it as part of your data. So in the approach with Joe, we say we want F to be right adjoint to E. We want to be given this adjunction, and we don't want to fix the other adjunction F left adjoint to E. We just want to say there exists an adjunction because actually it is there is a canonical one.
Some more questions? If not, we should thank Raphael and all the morning speakers for the interesting.